Hi, everyone. My name is Cong. I'm a software engineer at Google. I work on Kubernetes and the inference, and work very actively in the LLM-d community.
And I'm Maroon. I work in IBM Research. I'm leading the KV disaggregation workstream in Llm-d, and I contribute to the overall project.
And today here we are excited to show some of the awesome work the LLM-d teams have done on the PD disaggregation. And here's a brief outline of today's talk. We're going to cover some background on the LLM-d project and PD disaggregation. We're going to dive deeper into the implementation in LLM-d and follow that with benchmark results. And we're going to wrap up with some key takeaways. So what is LLM-d? So Simon covered LLM-d a little bit in yesterday's talk. So LLM-d is an open source Kubernetes-native accelerator agnostic inference stack. It offers you with streamlined, well-lit path user guides to get it started with reproducible benchmark results. So on the right side is a high-level diagram of the LLM-d architecture. On the top, we have an inference gateway that is capable of doing intelligent inference scheduling, such as load-aware scheduling and prefix cache-aware scheduling. On the bottom left, we have the inference pool, which represents a pool of compute resources to serve your models. And this is backed by popular inference engines such as vLLM. And on the bottom right, we introduce a new what we call variant autoscaler, which works seamlessly with the inference scheduler and the inference pool and takes into signals from those components and works with seamlessly with the Kubernetes horizontal pod autoscaler to scale your inference pool. So why LLM-d? So LLM-d is not just yet another inference stack. We truly believe LLM-d is the most open and brings the most standardization in the ecosystem. So for example, we try to reuse as much as possible the existing mature components in the Kubernetes ecosystem as much as possible. For example, the Kubernetes Gateway API and those Gateway API providers. And for the new components that we have to build, we truly advocate for open protocol and open APIs. For example, so we proposed this endpoint picker protocol in order to implement the intelligent request scheduling in the inference scheduler. And we work directly with the Kubernetes Gateway API community to have this native supported. So you're not replacing your inference gateway, your traditional Kubernetes gateway with a new gateway or load balancer. You extend your existing gateway to have the inference scheduling capabilities. And we proposed the inference pool protocol with capabilities like load-aware scheduling and PD disaggregation. And we work and contribute to the vLLM community directly to enable this support. And with all that, this means you will get the latest and greatest features of all those open components throughout the stack without being locked to a specific version or a specific implementation or a vendor. And this also means that the entire stack is highly customizable and composable with your existing infrastructure. So with LLM-d, we truly believe that you not only get the streamlined deployment in day one, but you'll continue to be able to evolve, to customize, and to operate effortlessly from day 2 and beyond. So some of you probably know that running a production-ready inference stack is not that easy. And that's where LLM-d well-lit passes come to help. So the well-lit passes are streamlined user guides and recipes with all the best practices built in. And we regularly test, validate these well-lit passes with CI/CD and benchmarks. So in each of the valid path guides, we will document in detail of the prerequisites of the infrastructure. For example, what are the accelerators, what are the network requirements in order to get the best performance out of this. And we offer general high-level tuning guidance on some of the key parameters you can tune to get the optimal results. And last but not least, we offer the recipes such as Helm charts, and we are Kubernetes-native, so we love YAMLs. Those YAML recipes, you can get streamlined deployment in like minutes. So here I will walk you through some of the valid paths we have today, and feel free to check out llm-d.ai, and you will see these guides in this website. So the first valid path, we call it intelligent inference scheduling. This will get you the intelligent scheduling capabilities such as load-aware, KV cache-aware scheduling, and prefix cache-aware scheduling with little to no tuning. So I highly recommend you try this out. Like, you will get the performance boost like out of the box. And under this intelligent inference scheduling valid path, we have a more advanced feature that is the precise prefix cache-aware scheduling, where the inference scheduler will talk to the vLLM or any model servers that emits the KV cache events and builds a precise index of the caches and route requests to the pod that has the highest cache hit rate. And another valid path, which Maroon will dive deeper into, is the PD disaggregation. In this valid path, we present with the Llama 7dB model and running on H200 GPUs. We actually demonstrate that in this valid path, we have different parallelism configurations for the prefill and decode workers. This is one of the benefits you can get from disaggregation. And our latest valid path, this is the wide expert parallelism or wide EP deployment with the DeepSeek R1 model, where you can get multi-host inference with leader work set. And yeah, shall we start talking about PD disaggregation? So in LLM inference, there are generally two phases. And the first phase is called prefill and followed by decode. Prefill is the process that the inference engine takes in the prompt and generates the first token, and also generates the so-called KV caches for each of these tokens. And this phase directly impacts an important metric called time to first token, or TTFT. So this is the time that you watch the spinning wheel of ChatGPT or Gemini and get the first word output. And in the decode phase, the inference engine will generate the output token one by one by taking into consideration of all the KV caches of the previous tokens. And this directly impacts another metric called time per output token, or TPOT. These two phases have very distinct characteristics. The prefill phase is generally compute bound, and the decode phase is generally memory bandwidth bound. And disaggregation is the idea that you can run prefill and decode in different instances. And why would you like to do that? Given the different characteristics, with PD disaggregation, you can tune and optimize and configure the prefill and decode independently. For example, PD disaggregation allows you to run different heterogeneous accelerators on the P and D workers. It also allows you with different parallelism configurations, which we actually demonstrate in the LLM-d PD disaggregation valid path. Now I'll hand it over to Maroon to dive deeper into some of the aspects of the implementation.
Yeah, so this part will be slightly more technical. Everything I'm about to show is well documented in the llm-d.ai website and GitHubs, so feel free to check it out there. We go over LLMD's implementation of disaggregated inference. So LLMD provides a tunable PD-aware inference scheduler. What that means is the scheduler is aware of the disaggregation. It plans the orchestration accordingly and it hits the execution. The execution is done by a routing sidecar proxy that is deployed alongside every decode instance. And internally, the communication or the transport of the KVs is done by utilizing the vLLM NIXIL connector, which I'll slightly get into in a following slide. But I think if you stay here for the next session, you'll get a better deep dive on NIXIL. So how does the inference scheduler work, or the PD-aware inference scheduler work? We have a concept of scheduling profiles in which you can configure the scheduler to how to make it select and rate the available pods. In this scheduling configuration, we have 3 profiles, one being the PD scheduling orchestration profile, which orchestrates the other 2, and the other 2 being the prefill profile and the decode profile. So the orchestrator begins with it orchestrates the 2, and the decode profile makes a prefix cache aware selection of a decode pod. So the pod it selects it both on load metrics and prefix cache aware metrics, but that means it knows how many new tokens it will have to prefill. And if the number of the new tokens is bigger than a configurable threshold, then it activates remote prefilling by activating the second profile, which is the prefill profile, and selecting a prefill pod based on load characteristics. The execution of this orchestration is done by the decode sidecar, and it sends. I'll get into that in a coming slide. So the scheduler orchestrates the selective PD disaggregation, and the sidecar executes it. So we have an example of one flow here. So if the number of tokens to prefill is bigger than the threshold, we make the selection, we send it to the sidecar with a few headers I'll get into. The prefill worker makes the prefilling, returns the request, and the decode continues. We see that in this diagram where you see the request coming to the sidecar, it sends the request to the prefill worker or the vLLM worker responsible for prefilling with a special header, which is do remote decode, max tokens set to 1. Once the prefiller is done working, it returns the response to the sidecar. At that point, the sidecar continues to the vLLM decode worker, also with special headers, being do remote prefill, the remote block IDs of the KV blocks that it needs to fetch, and the engine ID to identify the prefill worker. Once the decode worker begins execution, it doesn't block while getting the KVs. It continues serving other requests while fetching the KVs in through the NIXIL connector in a GPU direct manner, so GPU to GPU. Once the KVs are fetched, it serves the request and starts streaming the response back to the scheduler. A bit about the routing sidecar. So it's a proxy we maintain in LLM-d. It's deployed with every decode pod, not with the prefill pods. If you're not using PD disaggregation, it will do nothing. It's just a proxy that requests will go through. In disaggregation mode, it does what I just described. Also a bit on the KV transfer process. So the NIXIL connector is an implementation of the vLLM KV connector interface that Simon mentioned yesterday, if you were in his talk. The NIXIL connector is a NVIDIA Dynamo contribution. It stands for NVIDIA Inference Xfer library, which is a library for accelerated peer-to-peer communication in inference stacks or frameworks. Today, it's used for PD transfer, but we're working on evolving it to a general peer-to-peer transport for peer-to-peer KV cache sharing, which is a feature I think we'll have in LLM-d in the coming months. I'll go through some benchmarking data, but the overall consensus is it's tough to tune and it's not something you'll use for all your workloads. So what we see here is benchmarking data we put out in the 0.2 release. You can find it to depth on the LMD website, on the blogs. So this is a standard Pareto curve on a Llama 4 Scout deployment. It's deployed on 2 H200 nodes with InfiniBand RDMA enabled. It compares a standard deployment topology of 4 pods of TP4, tensor parallelism set to 4, and a disaggregated deployment of 4 prefill instances with TP2 and 2 decode instances with TP4. The scenario covers representative workloads with input to output ratios of 10:1 and 100:1. The x-axis measures the per user throughput. The y-axis is the per GPU throughput. We can see that at both ends, both deployments perform similarly, but in the middle, there's a clear and significant advantage to the PD deployment, because at these concurrency configurations, so the points are concurrency, I didn't mention that. In the middle, we see the scenarios where the contention between prefill and decode stages makes a significant difference. So PD exposes these saturation points and unlocks headroom for better performance. These insights are very critical to future work, for better auto-scaling, for workload-aware role assignment, so you can auto-scale your prefill workers or increase their numbers if you identify that your workload is prefill heavy, and vice versa. So these benchmarks and these insights are essential for unlocking better performance in inference in the future. This is a second set of benchmarking data on inferior or more inferior hardware. In here, we don't see a significant advantage to PD. We do see that it performs overall better, and especially at low concurrency points, if you look at the bottom right corner. But the point here is that getting value is not so simple. It's not easy to tune or easy to figure out how to get value out of these deployments, and that's exactly what we do at LMD. We have these well-lit paths. We have the PD well-lit paths that look into these deployments. We research these configurations and provide both data, deployments, and insights that you can use in your production environments. So these two PD paths we have are the PD standard path that I just described. There is the more advanced wide AP well-lit path that covers sparse, large MOE architectures. We do have good data there as well, and we'll be having more in the coming months. So I'll go over the distillation of our PD work, best practices we gathered over the past few months. So PD disaggregation is really not a target for all workloads. You generally should use it for large models, 70B plus, not like 8B or 1B. Long input sequences and long both input and output sequences, so think 10,000s and not hundreds. And sparse MOE architectures, where it gets a bit more complicated. So Cong talked about specializing PND workers for compute-bound against memory-bound workloads or hardware. But in wide AP, it gets a bit more complicated because you'll have to efficiently load balance your workloads across your data parallel or expert parallel ranks. So you wouldn't want some of your ranks doing decode and one doing huge prefill and locking all the rest. And there are also implementation details where you have specialized and optimized kernels for each stage. For example, in vLLM, there's a memory footprint versus CUDA graph usability trade-off, where you can have either a smaller memory footprint and no CUDA graphs, or high memory footprint and CUDA graph support. And naturally, these fit, like one fits for prefill, one fits for decode. So you have to disaggregate the two in these deployments so that they don't contend, and you'd have the specialization per each. So key takeaways: disaggregated inference is crucial for large-scale inference. Getting it to product or to your production environments is not trivial, but that's exactly what we do at LMD. Our research teams do it for you and provide the data continuously. And LMD enables Kubernetes-native disaggregated inference with production-ready well-lit paths. Thank you for listening. If you scan these QR codes, you'll get to our Slack and our GitHub. LMD thrives on community contribution. We invite you to look into our GitHub, pick any good first issue, and join the discussions. We'll also be running some demos of our well-lit paths in the Red Hat booth at about 1 today. Questions? Go ahead.
Hello. Thank you very much for the talk. It was great. So I have two questions which are essentially related. The first one is that what is the motivation behind going Kubernetes native? And the second one is about how do you compare LLM-d to the alternatives such as SGLang, which also has PD disaggregation, KV cache, and prefix-aware routing? Thank you.
So, okay, I'll take this one. So, sure. A lot of users already have their inference or their production environments on Kubernetes, and Kubernetes really excels at providing these capabilities. So LMD being Kubernetes native makes the switch seamless and easy. So you can scale up or get a better deployment with LMD simply by deploying it on your Kubernetes cluster. Maybe Cong has some input here, being from Google.
Yeah, I also want to highlight that some of the components, they are built with Kubernetes native in mind, but a lot of these components like the inference scheduler, you can actually deploy that as standalone kind of component and getting kind of intelligent inference scheduling capabilities out there. So I think in a way it's not like locked with Kubernetes, but we definitely want to make Kubernetes a first-class citizen in this ecosystem. Your second question about SGLang, so we have this sort of like inference pool kind of protocol that as long as the inference engine speaks this language and emits certain metrics about your load, doing PD disaggregation and understand those headers that Maroon talks about, LLM-d works with the inference engine, even it's your custom inference engine. We currently while it passes, we have vLLM tested and verified. We actually, for example, have verified the inference scheduling with SGLang. It works really well. So we work with we actually work with the NVIDIA Triton inference engine. So as long as they speak this protocol and they work seamlessly.
A question. I was just wondering, when you think about Kubernetes, it's a container. So I was wondering, in each Kubernetes, what is all included in that container? And are all Kubernetes having the same content or they're different? Second question is, you talked about prefill and decode, and you said this split enables accelerators to play. Can you give an example of what kind of accelerators could play in prefill and what kind of accelerators could play in decoder part?
Yeah, so I'll start with the second question. Maybe you can take the first one. So we have more data in our documentation on the well-lit paths, but I think it's more about optimizing the deployments. So decode being memory bound, you'd want higher TP, so you'd have more available KV cache or memory to pull your KV caches into. While prefill, you'd want more replicas, lower TP. So I think we also have data on specific hardware recommendations, but for that you'd have to check the website. Do you want to get the first question?
Yeah, also on the second one, I think one of the interesting data point, we don't have it today, but at Google, we're trying to, we have TPUs at Google, and we try to kind of mix and match TPUs and GPUs and get some results from PD. And the vLLM pass allows us to do that. On the first one, one of the principles we have when designing such, large-scale systems is to have, modules and components and with well-defined responsibilities. And when you look at LLM-d, it's not like a monolith container or Helm chart that you deploy. It composes of multiple components. So concretely, this means, for example, the inference scheduler, it is a container. We release that, we test that, and you can deploy. And vLLM is a container, and you can deploy it either with a standard Kubernetes deployment, or in the more multi-host, more advanced scenario, use leader workset, which is also a Kubernetes-native primitive you can use for multi-host deployments. It's not just works for inference; it works for any kind of multi-host deployments style. So in general, it's multiple components, they compose together. And we offer you with the recipes, with YAMLs, with Helm charts. You can deploy them together, and you can switch in and out. For example, if you want to use SELAN with no vLLM, and you can use that. You can do that too.
Okay, we're out of time. We can take questions on the side, and do feel free to join the Slack and have more enriching discussions.
Thank you.
Thank you.